I'm here to talk a little bit more about how we can actually use this data from Cassini to learn more about what's going on beneath the surface. Specifically, one of the things we can start to do now is look at variations in properties. And of course, people go like, well, each one of those jets is probably its own thing, but there are systematic variations across this that are important. And I'll just say this involves a cast of characters with different specialties and different instruments. It also involves postdoc Deepak Dhingra, who worked with me, who's kind of been one of the people taking the lead in understanding that material coming from Cairo, Alexandria, Baghdad, and Damascus are different. So the specific thing I want to focus on today is this dust to gas mass ratio. We all know that the plumes contain vapor, mostly water molecules, and solid particles of a wide variety of sizes. And that parameter is important in terms of how this stuff is generated and how its dynamics are. The annoying thing is measuring it, because basically any given instrument can only measure one of them. Every image you've ever seen is of the solid particles. The gas is pretty much transparent. All UVIS mostly sees is the vapor component because it's the dominant optical depth. So if you want to measure the dust to gas mass ratio, you need to combine data from different instruments, which is complicated, and especially because there's so much structure in this thing. You need to measure that dust to gas mass ratio at the same place and at the same time. There are a few opportunities to do that. Some in situ work had been done. I'm going to talk about one of the nice times we were able to do this with remote sensing. It's stuff that was recently published. And now we'll see if I can break this. Yep. This is from a solar occultation. So like we heard in the last talk, one way to study things is to watch a star pass behind the plume and see how it responds. The sun is a star, and it's very good at this. In late 2010, well, middle 2010, if you were sitting on the Cassini spacecraft, looked back at Enceladus, this is what the track of the sun did. It passes just below Enceladus. Enceladus itself doesn't block it, but it does pass behind the plume. So part of material in the plume will block some of the sunlight. And two instruments looked at this. One was UVIS. This is data from Candy's paper from 2011. Sorry, it's blown up so you can see all the pixels. This is the signal level without the plume there. This is the signal level when the plume's in the way. This is a drop of 30%. Got all this great structure telling you about jets, etc., and was published in 2011. So this is what's happening in the UV, and from their spectral data, they know this is mostly water vapor. There was another instrument monitoring sunlight during this time, the visual and infrared mapping spectrometer, which measured the brightness of the sun not at ultraviolet, but at the infrared, 1 to 5 microns. That data took longer to publish because it looked like this. This is a plot showing the brightness of the sun as a function of time again. This scale is 1%. It's very clean, actually. But there's not a huge drop in it. But if you look very carefully, right here, you see these 6 data points that are lower than anything on either side? Just saying the two colors are 2 different wavelengths. That is happening when we're closest to Enceladus. That, we think, is the scattering of light from the plume. It took us a long time to convince ourselves this was real. If you want to know that it is real, feel free to look through the paper and ask me, but I'm not going to go through tons and tons of statistical analysis and blah, blah, blah. What's cool about it and why it's important is this obscuration is not due to the gas, it's due to particles. The way we can tell that is we can look at the spectrum. This is probably the ugliest spectrum any of you have ever seen. This is the depth of that dip, plotted as a function of wavelength. Every plus in that graph is a single spectral channel. Fortunately, we have hundreds of them. The diamonds are bin data. And yes, the signal to noise is bad, but you can see that over a broad range, there is a signal. That's not what gas would do. Gas absorbs very well at specific wavelengths. This sort of thing is solids. It's dust grains in the range of about 1 micron. So we are seeing the particles. We are seeing something about the total amount of particles along the line of sight at the same time and in the same place as UVIS is measuring the total amount of gas. So the idea was we would compare these and get the dust to gas mass ratio. So what do you want to do? Now you want to plot your data. We can now plot VIMS and UVIS as different colors. This is now just measure of obscuration, optical depth. UVIS in blue, VIMS in red, makes sense. UVIS scale over there, VIMS scale over here. It's 100 times bigger. It's lower signal to noise, but it's not the same shape. You can also see that here. This is the ratio of the optical depths, which is directly related to the dust to gas mass ratio. And this is not a constant value. At this period, we see signal from the dust. That implies an optical depth ratio of about 1%, a dust to gas mass ratio of about 1. Okay, maybe it's 0.5, maybe it's 1. But in this early part, the UVIS signal is actually about the same. But the VIMS signal's gone. And that's significant. At this point, the optical depth ratio is now down around 0.1%. Maybe an order of magnitude less, maybe a factor of 2, depending on how you want to do it. Now, what causes that? Well, we already heard there's 2 different ways to explain this. One is it's a trend with altitude. The other is it's a trend with horizontal position. Altitude makes sense. We've already heard the particles are launched at different speeds than the gas. The particles are launched slowly, most of them. Those things go up and come back down. The gas mostly escapes. So a logical thing to think is here we're at lower altitudes where there's just more dust around. This is higher altitudes. And, you know, that's what probably I thought when I first made this plot. It's wrong. This puts those data in context. Got the same profiles up there, and down here we have a map of the South Polar terrain. You can see all of our favorite friends, Alexandria, Cairo, Baghdad, Damascus. These gray lines indicate where the line of sight was going over the surface, just a projection. This line shows where that line of sight was closest to the surface, which is where most of the signal is going to come from. This line is how far above the surface you were. Technically, it's the impact parameter, so it's how far you are from the center. But this is basically the surface. This is basically 50 kilometers up. This signal occurs here. Lowest altitude occurs here, where we don't see anything. This is inconsistent with altitude trends. It looks instead like, for reasons, Alexandria and Cairo aren't producing as much dust as Baghdad and Damascus are. And the thing is, since we're at higher altitudes, that difference we're seeing is a lower limit. Because if we went down something that might be the scale height of the particles, we might see correspondingly more dust out of there. There's a difference in the dust to gas ratio between these different regions. And the thing is, it's not just our data. You start looking in the published literature, you can find this all over the place. Remember I said, like, the in situ measurements measured this. they measured the dust and the gas during a flyby. Up there, I show the gas measured by one instrument, the particles measured by another. They're arbitrarily scaled so that they both have the same peak when the spacecraft was flying through over, basically, Baghdad. But if you look here, where they're flying over Cairo, now you have a lower dust-to-gas ratio. That's just like what we saw. They're seeing it at a different altitude at a different time, but it seems to be consistent. And as you go through other things, you find other trends. There's, hints of differences in the spectral properties of these different features. Again, Deepak Dhingra has looked a little bit at this. The surface deposits are different. Back in 2008, people made this nice map of the organic absorption signature over the South Polar terrain. And, it's a noisy map. This is where Damascus is. This is where Cairo is. That organic signature is higher over Damascus. And just to say, Candy did make one mistake in her talk. She said there's two types of particles. There's three. There's pure ice, salt-rich, and organic-rich. That's a distinct type. One time the CDA instrument flew over this region, this side had more organics. So there's difference, and again, all of this is in published literature. So there seems to be some sort of systematic trend across the Tiger Stripe region, where we have fairly gas-rich material over Alexandria and Cairo. So we have gas-rich over here transitioning to more dust-rich and perhaps more organic-rich, which might be interesting. What does this tell us? I'm not a geologist. I want to ask you what this is telling us. Is it telling us something about the difference between the plumbing connecting this to the subsurface reservoirs? Maybe. Or is it telling us these are tapping different sources? And I would leave it like that. I would love to hear people's ideas about this, because this isn't this is like mesoscale stuff in this particular region. So, thank you.
Questions?
Or answers?
Or answers.
Oops, sorry.
My feeling is that the geologists aren't going to be able to help you much. What we need are the submariners to tell you in the future what this means. But I can't, even though people are thinking that the ice shell is extremely thin for good reason, I still can't get out of my mind a thought that maybe that's misleading, that maybe the ice crust is very thick, but there's only a very, very thin, brittle crust, and that there's a very, very, very super soft, maybe Christine McCarthy softened ice shell below that, and that this is tapping into muck on the bottom of the ocean. I don't know.
I don't think
that's probably a stupid thought.
Well, that doesn't work with the silicates, which you need to transfer up from the bottom of the ocean somehow. I don't think you can do that through a mush layer, but I could be wrong.
Okay, hello. Okay. I had a question about whether those, I think it seems like, from my understanding, that you kind of lumped all the observations together.
Yep.
I was curious about whether you had looked at where Enceladus was in its orbit relative to each of those flybys, and whether that made any difference.
So we did. Unfortunately, these sorts of coordinated observations are obnoxiously rare. As Candy this was not near times of maximum particle activity on on that. It was at kind of a random orbital phase. We thus far have not tried by going through this thing to identify, we've kept going, oh, maybe we'll see something here and something there. This is already a variation, and then we have a variation in the, temporal thing. Trying to measure the variations of the variation is something that really needs to be done, but we haven't been able to do anything systematic that covers that.
I was just going to encourage you maybe to chat with someone like Terry Herford, who's done a lot of the tidal stress orientations. So, because it might make a difference to what's turning on and what's not turning on as you go across. But also, I'd just like to say something about those calculations, to pay attention to what's happening with depth as well as at the surface, because it's true that, and this was brought up earlier, that we can't just think about what's happening at the surface in terms of tidal stressing, that we need to think about it with depth. And then I would say, as the semi-geologist, that maybe that is allowing it to tap into different areas in the crust, and might be bringing up certain things from certain depths at certain times because of the differences in the tidal stressing and things like that.
No, I definitely agree on that sort of thing. And just to also say, I think one of the things to do now is we know the particle flux does change. One of the things, at the level of individual sources, the tidal flexing doesn't seem to necessarily explain all the variations that are seen. Like individual sources seem to turn on and off fairly randomly. That was work before us. I think it might be time to say, oh, how does Alexandria go with orbital cycle? How does Cairo go with orbital cycle? If these are different, that would help understand that, because maybe the lag is different for Baghdad than it is for Cairo, and that's telling us the depths are different. That's not something I personally have.
Right, but you team up with these people, then.
Yeah. Right. But I do think, I'm just saying, I think there is scope for a little more information there as well. Yep.
Fascinating work. I guess the solid to vapor variations across the system doesn't worry too much, because in my mind there's sublimation going on as well as cryovolcanism, and that's easily explained. But this organic to salts ratio is a bit new to me. Yeah. Could you clarify how extreme that is? I mean, that's a real strong signal.
I would say that is still a bit of a question. So this map is all that's been done on this. I have not. This is a weak absorption band. So, and it's a deposit. So the question of how it behaves is a little requires lots of photometry and all sorts of fun things, which maybe I will do. The dust detector comes from another single flyby. So this is the flyby that, these are the three different types of grades. Pure water, salt rich. This is the trajectory of the spacecraft. It started off very close to the plume and then flew up. As it entered the plume, the water ice fraction went down, the salt rich fraction shot up. That was indicating the salt rich are all trapped at the bottom. This plot is in the paper. The organic rich fraction starts here, and as you're crossing the plume, it's slowly rising, even though you're moving out. And these particles are almost as big as these. You need to do, again, a proper dynamical model for understanding this, but this might be a way to say how much of the organic rich particles are in these different ones. But the problem is them doing compositional measurements is really hard on an Enceladus flyby. They have only a few times they've done it, and this was the one time it was cross the tiger stripes, which was, if you want to look for trends along a tiger stripe, that's harder.
So from a subsurface point of view, I can think of two possible explanations. One is that you have depleted volatiles more from one part of the source reservoir or one of the source reservoirs than the other. That would be to some extent supported by the ratio of water ice grains to organic rich grains. The other is that there is a slight difference in transport mechanisms going on from the subsurface to the surface. I'm not sure we can get to the bottom of that with the data, but I'll think about it in modeling.
Okay.
Okay. Is everybody ready for coffee time?
Coffee.
Oh, wait. Bill's not ready for coffee
Bill's
time.
not ready for-
It's Bill's fault.
Sure.
I love coffee. I'll just point out one more thing. 2 weeks ago in this very room, there was a nice presentation by the CDA team on, in fact, a new paper that they're submitting or have submitted on these organic grains.
Yeah.
And you can look at their abstract.
Okay. Yeah.
For anybody else, I don't have the paper, so don't ask me. But you might contact them.
No, they've definitely been making a lot of progress on these organic rich grains, and
Yeah.
I'm glad to hear their paper is finally coming out.
Yeah. Well, so I think it's submitted. I don't know if it's.
Yeah.
We must presume though that it will.
Yes.
Come out. Okay.